So we talked about the summary statistics from ex post perspective first, and we added the ex ante perspective and interpreted sample statistics in some statistical context. Now we can do the same thing about OLS, the ordinary least square. There are a set of things that we can talk about ignoring all these statistical concepts, and that's what we will do here. And there are things we can talk about in the ex ante perspective. So what is OLS? Again, let's use exactly the same example where X is individual heights, and Y is mother's height. With the ordinary least square technique, what we do is we want to describe again the data. We want to describe the relationship between X and Y in some way. So we can think about a plot, scatter plot of X and Y. And if we have data on X and Y for 100 people, then for each person we can indicate each person as a dot. So if we have observation on 100 people, maybe we will have 100 dots here. So one way to summarize the data is, of course, just to make this plot, scatter plot, print out and just distribute. That's a good way to summarize the data. So that's useful enough in some situation. If you are interested in whether X and Y are strongly related, then you can just look at the graph and say perhaps there is a strong relationship between X and Y, and perhaps there is no relationship between X and Y. So to some extent, drawing a scatter plot is enough as data summary exercise. So, and that's what people do. They first draw scatter plot. And if you are not satisfied with the scatter plot, if you want to say something a bit more specific, then what you can do is you can think of a line that represents all these points well. So if you can think of some line that represents the points, perhaps in this example you will come up with a line like this. And since this is a line, you can represent this line as a linear function. And again, here the goal is to summarize the data. And there are many ways to determine this line. There are many ways to determine the values of A and B. And ordinary least square is just one of many possible ways of determining this line. And in OLS, the way we determine this line is for each point, we calculate the vertical distance. So if this point is xi, comma yi, then for some A and B, this vertical distance will be just yi minus A minus B xi. And what we do is we square this distance. We square this and take the average. We don't really need the average. And sum this quantity for all points. And we find A and B so that this quantity is very small, the smallest. And that's why it's called least square method, because we have square here and we want to minimize this squared value. And if you can find A and B, if you find A and B from that calculation, and that A and B and this equation is called the least square solution to this problem. And that process is called ordinary least square method. Again, let me emphasize that this is just technique. There is no assumption involved. There is no probability involved. We don't even talk about random variable. This is just pure algebra exercise. Okay? So you can always do the ordinary least square if you have two variables and data, some numbers, then you can always do this. And from here, only from algebraic perspective, so once you determine A and B, this equality is of course not satisfied, because what we did was we minimized the distance between this part and this part. So there will be some extra term, and we call this extra term residual. And what we did is we found A and B so that the sum of squared residual is very small number. That's what we did. And also this residual is perpendicular to the regression line that we made. And from the construction of A and B and E, we also have this particular relationship which is always satisfied, and that's how we determined E. So given this particular property of least square residual, if you calculate variance of yi here, then since yi equals this 3, we can apply the property of variance that we discussed earlier. A is constant, we can ignore. So we have two terms. So we have variance of this, covariance between these two. But covariance between these two becomes 0. How do you know? Because of this property. So in the end, after you determine the least square regression line, variance of y must be always equal to b squared variance of x plus variance of e. And not to confuse you further, let me drop the I subscript, because when you add I subscript, it's a bit confusing what we are talking about. So what we are doing is we just calculate variance of all the y data, we calculate variance of all the x data, and we calculate variance of the residual determined from this equation. And B is found through ordinary least square method. So after determining A and B through ordinary least square, and this is the relationship we always get, and the interpretation is the variation in y has two components. The first part is related to the variation in x, and the second part is not related to the variation in x. And to the extent that this way of writing down the relationship is useful, this is more interesting part. So this part we can at least interpret this as something to do with x. this is something we cannot really interpret. This is just unrelated to x. So we consider this. If this number is higher, relatively higher, then this suggests that the regression line is summarizing data well. And for that, we calculate this ratio, which is always less than 1 because we drop this part. We call this R squared. And we use this R squared as showing whether regression line is close to the data points. If R squared is low, then regression line, data points may be far away from regression lines, because this residual, in fact, is indicating how far away each data point is from the regression line. Okay.
그러니까 2가 0이 아닐 때, 그러니까 2가 0이면 저기 1이 되잖아요, R이. 근데 그래서 이제 2의 영향에 의해서 그 기울기가 결정된다는 거예요.
Because the first part is correct. So if every point is on the regression line, then this will be always 0 and this will be 1. So that indicates perfect fit. In general, the points will be away from regression line. This number will be different from 0. So this number will be some positive number, and R squared will be less than 1. So just to talk about two extreme examples. If the data you have is like this, then when you find the regression line will look more or less like this. So R squared will be very high, close to 1. But if the data points are like this, perhaps you will get exactly same regression line. Sorry, it won't look like this. But here, many data points are far away from the regression line, so R squared will be low. Did I answer your question? Okay. Any other question? So the R squared, okay, to emphasize this ex post perspective once again. So R squared is the concept that is not related to the random part of the analysis. We can talk about R squared without talking about probability at all. So R squared has nothing to do with the probabilistic interpretation of ordinary least square. Okay, so when you talk about OLS, you have to distinguish again between ex post perspective and ex ante perspective. And what we described here so far is it's something to do with ex post perspective. There is no statistical, probabilistic, random something here. It's all about algebra.